All right, good morning, everyone, and thanks for the invitation to come here and give a talk. It's kind of fitting I went after Karsten and Richard because without them, this talk probably wouldn't exist. So just some history, I postdoc with Karsten for 3 years when he was in Munich, and that's where I got into all this implicit solvation stuff. And originally, my goal was just to take VASPsol that Richard had developed and add a nonlinear Poisson-Boltzmann model to it, one of Stefan Ringe had developed in Karsten's group. But it turned out into a complete rewrite of the code. So we had to give it a new name. We call it VASPsol++. So I'm going to talk a little bit about that, but more in general, I'm going to give an overview of kind of where we are right now in the field with implicit solvation models, what they're good at, what we can do with them now, and where we need to go in the future. So, Karsten and Richard did a lot of my work for me, so I don't need to give a lot of the background. Basically, if we want to model electrocatalysis, we need to get the electric field at the interface right because the surface charges, we get this double layer. And Karsten mentioned adsorption energies, which, yeah, it's important for adsorption energies, but if you want to calculate barriers, then it becomes really important because you're doing things like transferring a charged species, a proton, across this interface. And that electric field is actually what pulls that proton across the interface. That's your driving force. So we have to get that right. Since we're modeling bond breaking and formation, we do need quantum mechanics, DFT, to describe that. But at the same time, we need statistical mechanics to describe the different configurations of the electrolyte. So this creates a kind of a difficult situation. And let me just kind of come back to the whole theme of this workshop. It's bridging the gap. We've been talking about how we need to bridge the gap between dynamics and statistical mechanics, which is basically stochasticity. But in my mind, there's an even bigger gap. It's the gap between classical mechanics and quantum mechanics. If you want to describe the electrocatalytic system efficiently, you really need to do it at both levels. Sure, you can do AIMD, describe the whole thing quantum mechanically, but that's brutal. It's also overkill just because you're describing a lot of stuff over and over, kind of recomputing the same quantities over and over and over again. And obviously machine learning can help accelerate this, but I'm kind of looking for a different approach, a more, I kind of take Karsten's view, but in an even more extreme view that I really want to be very physics approach, coming straight from first principles. So yeah, I mean, you can use AIMD for this, but it's not really appropriate for complex reaction pathways like CO2 electrolysis, where, as I'm going to show you some of our results, you have something like 50 barriers you have to compute. That's just not going to cut it. And really, the whole difficulty is that electrocatalysis lives right in the middle of all of this. So we kind of have to deal with all four of these aspects right here. It's right in the middle of this mess. So the way I've structured my talk is kind of the past, present, and future. The ways that we've tried to overcome this and actually do something to model electrocatalysis and get something that we can get insights out of or just publish. So I'm going to start with the past, the computational hydrogen electrode, limiting potentials. Karsten touched on it. It's going to be very brief because it is in the past, and I prefer the past stay in the past. Then I'm going to go into the present, where I'm going to talk about how we've improved some of these implicit solvation models, combined them with a hybrid approach to simulate these electrocatalytic reactions, calculate barriers of these huge reaction networks. And then I'm going to get into the future. What's the next step in implicit solvation? And I'm going to introduce something that I've developed called the implicit quantum that should be electrolyte, not electrode. The electrode's obviously quantum. So I'm going to talk about that at the end. And that's an idea I've had. It's not something I've implemented yet. It's an idea, but I think this workshop is the appropriate place to present something like that, just to kind of get discussions going. So the past, as Karsten laid out, we've got this computational hydrogen electrode. We reference everything to gas phase hydrogen, the chemical potential of the coupled proton and electron. We compute these free energies of all these intermediates. We calculate the potential where all these steps become downhill, and then we define what's called this limiting potential. It's the minimum over potential necessary to make all the steps downhill. And people have used this approach to screen catalysts, and the idea is that the lower the limiting potential, the more active the catalyst is going to be. But this assumes that all the barriers are very small. The problem is that these barriers aren't small. For example, in oxygen evolution, the barrier to form the OO bond, it can be up to 1 electron volt, which is not trivial. Compared to these barriers that just involve simple proton transfer to an oxygen, which is basically just shuttling protons across a hydrogen bonding network. So we need a way to compute these barriers. And that's where I'm going to get into the next part of the talk. Yeah.
You go back one.
Okay.
I mean, I think, Jan VASPsol has done a very, what I think is insightful description of OR and ORR. And shown that really the overpotential of 0.3 that you get is really due to a difference in binding of different species like OOH versus OH. And not so much a barrier. I mean, you can think of it as like something you have to overcome, but it's not really a kinetic barrier.
Yeah, I would. So it definitely correlates. There's a reason it correlates, but I would say the barrier is actually really important. It's because the barrier obviously depends on the energetics. If you make this step more downhill, the barrier is going to decrease.
I can see Carlos is getting agitated, but I would say, like, I think it's very easy to work that this 0.3 difference, this overpotential that you have to apply to make things downhill, to me is very compelling. And the fact that we can't get around it because, OH and OH bind in a very similar way.
Yeah, no, you're absolutely right that the constraints, these scalar relations, still hold. That part doesn't change.
So I would challenge you to tell me where the barrier, the actual barrier, is important in that analysis, because I think you've done a beautiful job to explain the limitation. Yeah, go ahead.
Graham, do you mind if we talk after? Because this could be a pretty lengthy discussion.
Just very briefly, I mean, thermodynamics, you have to get it right. And I fully agree with you that Jan and Jens did a great job in this. But there are actually quite a lot of reactions where the kinetics on top of it make sense. So just for this to go thermodynamically downhill is just not good enough. In particular, not for selectivity. For example, just that on the gold electrode, the hydrogen peroxide, we just published an ACS-Catal, it's all the barriers, and they didn't have it. So I think I stick with Team Craig.
Okay, but on this one, I think you've done a very good job explaining it and the challenges. And no one can get around that 0.3 that I know of.
We published a paper on it.
No one has a catalyst that has an overpotential that's less.
Okay, you're right about that. I'd say the part that's right is that part's right. I would argue the reasoning is wrong. It's not completely wrong, but there's some things it neglects. But again, I think we could probably go on for half an hour with this. And anyway, if I don't calculate barriers, I can't use your awesome methods either, because we do use dimer and NEB. All right, yeah, that's all. I should have just said that to begin with. Okay, so now people have been using this for the past 20 years to do these thermodynamic studies, but now we want to start being able to calculate barriers. So we need some minimal description of the solvent. And Carsten already kind of laid this out. The implicit model is the easiest. And I kind of gave some of the background behind VASPsol++. We basically wanted to put these nonlinear effects into VASPsol so that we can get these kind of double hump capacitance curves that you don't get with the linear model. Other issues is that you see what's called solvent leakage. The implicit solvent will leak into places you really don't want it to go, like in between water molecules sitting at a surface. And then there are also some numerical issues that we wanted to iron out, like the need for these high plane wave cutoffs and difficulty in SCF convergence. So we implemented a nonlinear and a non-local model of the electrolyte to overcome all these issues. And we basically rewrote we kind of took the original structure of VASPsol, completely rewrote it with all these different additions to it. So to start off with, like Richard said, we have this free energy functional. And I'm all over the place in my slide. I use A's, F's, G's, depending on which part of the talk I'm on, so bear with me. But this A is the same omega that Richard was using. So we say that the total free energy consists of the cone-sham part. That's just the part that comes from DFT. Then we've got dielectric and ionic screening terms. And these account for the dielectric and the ionic response of the electrolyte to any kind of field or electric potential. And then we have this cavity formation energy, free energy. That's basically just the energy, this tau that Richard was talking about, the energy to form the cavity around the solvent or the surface. So in our model, we have several degrees of freedom. We have the solute electron density and the potential, which we would normally have to solve for anyway without implicit solvation. Then we've got the solvent degrees of freedom. We have a solvent rotational distribution function. It's basically the probability that a solvent at this position is pointing in this direction. We also have an internal polarization that accounts for the electric and ionic polarization of the water molecule, and that depends on the position. And then we've got these ionic degrees of freedom that basically quantify the occupancy of ions at different points in the electrolyte. So the way that we implement this is...
So this is all just for planar surfaces, right? So
it could be anything.
if you have a molecule, how can you describe a solvent rotational distribution?
So it basically, if you look at the derivation of the original VASPsol, it kind of starts this way. It's just you integrate over everything. You linearize it, and it kind of integrates out. But I mean, it's just at every point in space. It's basically it integrates out to the polarization, like this polarization field. Okay. My clicker thing. There we go. Okay. Okay. So before I get into what each of these, like how we implement each of these terms, let me talk about the cavities, because one of the key things that we implemented was a non-local cavity definition. So I mentioned the problem of solvent leakage. That happens because the model doesn't know that water has a finite size. It thinks it's a point particle. So what we do is we first define what's called a van der Waals cavity. It's basically the cavity that's in VASPsol. It has this NC cutoff. It's an electron density cutoff. It's 0 inside the cutoff, 1 outside the cutoff. It slowly ramps up it's a step function that Richard showed. But then we do something else. We push it out by a distance called the solvent radius. It's basically the radius of a hard sphere water molecule. We do the same thing with the ionic radius. We push it out a distance equal to the ionic radius, and we get these two new cavities, the solvent cavity and the ionic cavity. And the solvent cavity and ionic cavity, they basically describe where the centers of the solvent molecules and ions are allowed to go. But the problem is that ends up pushing things out too far, especially for the water, because water it's not a point particle. So the bound charge is not localized at the center. It extends out a distance. We call that the dielectric radius. So once we have this solvent cavity, we push it back in distance equal to the dielectric radius to get this dielectric cavity. And the dielectric cavity tells us where we get the dielectric response of the solvent. Okay, to get the nonlinear dielectric free energy, that's that second term in the free energy functional that I showed, we use a rigid rotor model for the water molecule. So basically, we assume that the water molecule at every point in space can be pointing in any direction, and we assign a distribution function. And getting back to Carson's question, it doesn't matter how we orient it. It's rotationally invariant. And this distribution functional, it depends on the position and the orientation. And we define a rigid rotor entropic free energy that depends on these distribution functions. We have a normalization constraint because it has to normalize to 1. And then we add a internal polarization energy. That basically reproduces the optical dielectric constant of water once the rotational modes are frozen out. However, we have to add back one thing. We have to add back this self-interaction and correlation correction, because a molecule of water doesn't interact with itself. It's also correlated with water molecules around it. And if you just use these terms, you don't include this, you won't reproduce the dielectric constant of water. At least not with physically reasonable parameters for like the dipole moment and the density of water. So we have to include this term as well. And then finally, we have the interaction with the electric field. And then we can define the net polarization of a solvent molecule by integrating an orientation vector over this orientational distribution. We add the internal polarization, and we get the polarization at every point in space. And that's the quantity that we actually need. We don't actually compute this rotational distribution function. It just goes into the definition. For the nonlinear ionic free energy, this was all based off of Stefan Ringe's work. And we do what's called a translationally invariant lattice gas model. So there's not actually a lattice there. All it means is that our free energy functional has that form. We have site occupancies. Every site can be occupied with either a cation, an anion, or just solvent. And we have a translational free energy term that accounts for the entropic effects. And then we have a normalization constant because they all have to add up to 1. And then we include the interaction with the electrostatic potential. And we can define a net charge of every electrolyte site as just the anionic occupancies minus the cationic occupancies because in my world, electrons have positive charge because that just makes everything easier. And the crucial thing here is that the ions have a finite size. The ionic diameter. And this keeps them from packing, especially when we get these nonlinear Boltzmann distributions near a highly charged interface. If we don't have that, it'll blow up. We'll get extremely high unphysical charge densities.
So what is the size or this distance? Is this related then to the solvation shell? Or is
Yeah.
it related, so it's not really the covalent radius?
Right. It's like the solvated
larger,
radius.
it's really the solvation, so that...
Yeah, exactly. It's the same thing they use in FHI aims. It's basically the same approach. Okay, so once we have these terms, now we need to compute the ground state dielectric and ionic response. We do that, like Richard showed, we take these functional derivatives with respect to the degrees of freedom, set them to 0, and that allows us to solve for the rotational distribution functions, the ionic occupancies. And from those, we can compute a polarization at every point in space and a charge density, ionic density at every point in space. And if we plot these responses, we see that they're nonlinear. If we only had the linear terms, we would just have this region here near the origin. But you can see that the dielectric response saturates as we get to high fields because once all the water molecules are pointing in one direction, you can't orient them anymore in that direction. It's basically saturated. With the ionic response, we have kind of this S-shaped curve because we get this Boltzmann effect, this Boltzmann distribution effect, the exponential effect at low potentials, at least when we have a dilute electrolyte. So the response actually gets enhanced by this. But then it starts to saturate as we approach the maximum ionic density based on the ionic radius. So both of these exhibit this saturation kind of behavior.
Great. What are the units on the axis? So when do things really start to saturate?
So the units, it's all dimensionless. This is units of related to Boltzmann, to KB times T.
So for room temperature, roughly, did you check roughly where the field is, where this starts to?
Yes. So we've applied this. We've calculated it for surfaces, and we do see saturation happening at highly polarized surfaces. You know, something you would have like during CO2 reduction, like -1 volt. Okay, so that was how we got the dielectric and ionic responses. The other thing we need to know is the potential. So in VASP, the potential's easy. Without solvation, you just solve the Poisson equation. Now, though, we have some complications. So what we do is we take we take the functional derivative of the total free energy with respect to the electrostatic potential phi, But now we get terms not only from the cone-sham free energy, but also from the dielectric and ionic free energies. And these give us the bound charge and the ionic charge densities respectively. And these are nonlinear in the potential or the electric field. So solving them becomes very challenging. And this is where I basically copied the approach of Stefan Ringe and linearized it around a given solution of the potential. So, say we guess the potential at every point in space, or we initialize it, we linearize it, the bound charge and the ionic density around that point. We actually, like Richard showed, we get this, this is kind of similar to what Richard showed, except instead of a scalar susceptibility, we actually have a tensor susceptibility. That's due to the nonlinear nature, because it polarizes, the susceptibility is different in the direction that most of the water molecules are pointing in versus the perpendicular direction. We do the same for the ionic density, and we get this effective inverse Debye length. And then we can use it to construct this linearized Poisson-Boltzmann operator. Everything nonlinear then goes on the right-hand side and defines this nonlinear Poisson-Boltzmann residual. So now what we can do is at every point, we get this linear problem that we can solve to get the kind of a step direction. So what we do is we linearize it around a given potential. We use a linear conjugate gradient to solve for this search direction that satisfies this equation at constant value of the potential. Then we do a line search along that direction. And the line search is critical. Without the line search, it doesn't converge, because you kind of have this pathological shape of the response curve. It's like if you ever took a numerical methods class, it's when like the secant method doesn't converge. So we have to do this line search. And after we take a step along the search direction with the line search, now we get a new potential and we just do the whole thing over. So it's basically a Newton solver block nested around a linearized conjugate gradient block. Okay, so some of the important properties for electrocatalysis that we'd be interested in if we want this model to be able to actually give reasonable barriers and energies are things like the solvation energy of the self-solvation energy of water, the solvation energies of hydronium and hydroxide, the auto-ionization energy of water, the Helmholtz capacitance of a typical metal electrode, and the potential of the standard hydrogen the vacuum potential of the standard hydrogen electrode, and the work function of an electrode. So the one parameter that really matters is the dielectric radius. All the other parameters we can fit fairly well to physically based quantities. But this dielectric radius, we really can't. So what we did was we tried several different quantities, increasing it from 0.9 to 1.5 angstrom. And we looked at how these different quantities vary. So the zero line is the experimental values of all these. So every time one of these curves crosses the zero line, that would be the ideal value of the dielectric radius to reproduce that property. The problem is you can see they all cross at different points. So we can't simultaneously reproduce all of these. We can't simultaneously get the pKw of water, that's the auto-ionization free energy, at the same time that we get the water self-solvation energy. If we increase the dielectric radius enough that we do reproduce the auto-ionization energy of water, the self-solvation energy is way overestimated. Part of this is due to bound charge penetration. So what this means is that when you polarize the electrolyte, you get bound charge. And that bound charge is really the kind of the electrons on the water molecule. I mean, it's really it's a rotation. The water molecule is changing orientation, but it's really due to the electronic distribution on that water. And the electrons, they can't actually penetrate the electrons on the surface because of Pauli repulsion. But the problem is in this method, And in any implicit solvation method currently out there, they do. And you get pretty severe penetration depending on the parameters you use. And I didn't show this in this talk, but normally you cancel that out by adjusting this effective surface tension, this tau parameter Richard was talking about. And in most of the models I've looked at, it tends to be way higher than it needs to be, than it should be based on experiment, precisely because you have to cancel out this bound charge penetration. Okay, so nonetheless, though, it's not all that bad because we do get the auto-ionization energy reasonably correct when we're at a value of the dielectric radius that matches the experimental water self-solvation energy. I think the pKw we get is around 17 compared to 14, so it's off, but it's not terrible. Okay, so now I'm going to show how we applied this to calculate kinetic barriers for various electrocatalytic reaction steps. So I fully agree with Karsten that when he said that these implicit solvation models are not suitable for computing barriers of electrocatalysis. But with one caveat, that's when you use them by themselves. We developed a hybrid solvation model where we include explicit waters in the calculation. So if you have something like the Fulmer reaction where you have hydronium and it's transferring a proton to the surface, that hydronium is highly solvated in the electrolyte. It's hydrogen bonded to 3 water molecules very strongly. These are not electrostatic bonds. They're really almost covalent. And the implicit electrolyte just can't reproduce those. So we include a few key explicit waters in order to form these strong hydrogen bonds, and that allows us to calculate transition states. So this is a transition state for the Fulmer reaction. You can see that the hydronium is transferring a proton to the surface, and it's stabilized by 2 explicit water molecules. And if you don't put those in, then you don't get a barrier. The proton just transfers spontaneously. The other thing we have to do is we're doing all of this in a grand canonical formalism. I didn't mention it, but VASPsol++ can do calculations at constant potential. So the charge is fluctuating it's not fluctuating, but it's adjusting during the calculation to maintain a certain Fermi level or work function. So we're in this grand canonical formalism. So basically we have to account for everything that can go into and out of the simulation cell. The important things are we have electrons, so we have to define a chemical potential for those. We have protons. We have chemical water. Yeah.
Can you say a little more about that? Like, do you have an extra loop there to?
Yeah. It's not an extra loop, but we put it into the ionic loop.
You change the number of electrons in the whole system?
Yeah.
Okay.
Well, like every step of the ionic loop. We don't do it during the SCF.
So your system is periodic or not?
Yeah. This is all in VASP. So yeah, it's a plane wave code.
I have a couple of questions then technical. How do you really, because you have a unique Fermi level across the system.
Yeah, we can definitely talk about that after. It's again one of those things that can be a long discussion.
Sorry, one other quick clarification though. It's electronically grand canonical or ionically as well? Like you're also exchanging
ionically too.
Okay.
Yeah. Because actually the charge is always neutral. Whenever electrons flow in, the ions flow in to screen it. That's how we get, maybe that was your question, because the cell itself is always neutral. Okay, so we have to
measure the potential drop essentially.
What's that?
You say measure the work function essentially.
Yeah, exactly.
So yeah, okay, makes sense.
So the other species we have to consider are what's called chemical water. So chemical water is water that actually participates in reactions. In comparison to explicit water, which I call W. These don't, they just participate in hydrogen bonding, and we use different chemical potentials for them. And if we're modeling something like CO2 reduction, electrolysis, we also have hydrogen on the surface. So we also have a reservoir of absorbed hydrogen that can flow into and out of the cell. I mean, it's already on the surface, but it can redistribute into and out of the simulation cell because it's really an infinite unit cell. So we define chemical potentials for all these. For the for the proton chemical potential, we use this reaction. We take hydronium, remove 2 protons, and get hydroxide. And we define the proton chemical potential based on this with a pH correction. That exactly reproduces the neutrality condition of water at pH of 7. That's why we choose that approach. For the explicit water chemical potential, we take a water hydrogen bonded to 4 explicit waters in a simulation cell, and then we remove those explicit waters and leave just a single water in the implicit solvent. And all of these are an implicit solvent. And ideally, that energy should be 0 because the water should be equally well solvated by the implicit solvent and by the explicit solvent molecules. Otherwise, you end up with thermodynamic inconsistency when you form or break these hydrogen bonds. So we define the water chemical potential, the explicit water chemical potential, to match this condition. Then we can use the computational hydrogen electrode to define the chemical potential of the proton-coupled proton and electron. And if we know the proton chemical potential in this, we can get the electron chemical potential. Finally, we want to compute free energy diagrams in this grand canonical formalism. So what that means is that we're going to be simulating different states of the surface with different adsorbates and intermediates. We need to compute the free energy difference from some reference state. So first we define the I call it omega here because it's a Landau free energy. It's in a grand canonical ensemble. It's composed of the SCF free energy. We get ZPV, vibrational free energy. Then we have these terms, this one should have been a minus, that account for adding and removing water, adsorbed hydrogen, and protons and electrons out of the system, coupled protons and electrons. The electrons themselves are contained in this, this omega SCF term because this comes from VAS. It already subtracts the number of electrons by means of just the net charge in the system. And you see if you add these together, you end up getting all the individual pieces that I laid out in the previous slide. Then once we have those, we calculate the chemical potential of every intermediate on the surface. So for a given intermediate Si, we take this free energy with respect to a reference surface, and then we subtract off all the species that we had to add to the system to get to that intermediate from the reference state, basically just balancing the chemical reaction. And it's the one thing my students have the most trouble with, but it's really just basic high school chemistry, just balancing things.
Maybe a question. So why do you call this chemical potential? It should be something like a formation energy, right?
Yeah, it's the same thing. I mean, in thermo, like it's the
formation energy. I would not call it a chemical potential. So therefore.
Technically, it's the change in the free energy when you add that adsorbate to the surface or intermediate. Yeah. So it's a.
Would be the chemical potential needed in order to make this formation happen, or so. Look at from this side. So then. I mean,
I'm basically defining the chemical potential as the derivative of the free energy with respect to the number of these species on the surface, right? So it's like the change in free energy when I add one of them to the surface. But yeah, I mean, it really just comes down to, it's just a notation. It has the same meaning that you're talking about. Okay, so now I'm going to talk about a few applications of this that we had. So the first thing we did was we used it to compute electrochemical barriers of the Fulmer step on copper 100. And we used different proton donors. We used hydronium, we used water. So hydronium is the proton donor in acidic conditions, water is the proton donor in alkaline conditions, and we use different phosphate anions from phosphoric acid, H2PO4 minus, HPO4 2 minus. Because in CO2 electrolysis, a lot of the times these buffering agents are in the electrolyte and actually participate in the proton transfer reactions. So we computed all these barriers as a function of the RHE potential. And you can see that obviously, as the potential gets more negative, most of these barriers go down. The two exceptions are the ones that have a negative charge on them. They do go down, but then they start to go back up. And the reason is because the surface is charged negatively. It's a negatively charged species, so they repel each other. Yeah.
Quick questions about your geometry or your layout of the supercell. So the implicit solvent is going possibly to the back surface?
Yeah.
Or do we have a vacuum in between?
It's going all the way to the
You
back.
have, okay, and it's an asymmetric surface? so-
Yeah. Yeah.
How do you insert water?
What do you mean by insert water?
I mean, I don't understand how you can be fully grand canonical if you have explicit water. You say that you can actually insert ions in everything. I mean, this is totally dense. Your acceptance ratio is super zero, and you would need further sampling before you actually can make a decision whether you add more or remove more. Right? So there's an entire Pandora's box in how you can actually become.
Well, it's not really that. I mean, so we're not doing it. It's not like a Monte Carlo simulation. This is a very simple approach where we're manually. I think you said in your talk, we're just manually adding different numbers of waters and then taking the lowest free energy structure.
So it's not fully grand canonical. You're doing
Right.
many different canonical simulations at different stoichiometries,
exactly,
and then you
yeah.
compare them a posteriori.
Yeah.
All right. Okay.
Yeah.
Then I'm.
Yeah. I mean, the only thing that's truly grand canonical is the electrons and the counter ions.
That's simple.
Yeah. Okay, so, and the other thing is, the key point is that we found that as you go to proton donors that have a higher pKa, the intrinsic barrier increases. So hydronium has the lowest barrier, then phosphoric acid, water, and then these other phosphate ions have somewhere in between or sometimes even higher just due to their negative charge. It kind of breaks this relation.
Another quick question regarding the geometry. So all the water molecules are fully relaxed?
Yeah.
Okay, so it's kind of a static picture that you have.
Right. Yeah, these are just static DFT calculations, optimized but static. Okay, so the final application I want to talk about is where we applied it to electrocatalytic CO2 reduction on copper. So we kind of know how this first part works out, CO2 to CO, but how we get these different C2 products is really, it almost seems like the mechanisms obey quantum mechanics, and you can have like every mechanism happening at the same time if you read the literature, as Carsten alluded to. So we wanted to figure out what determines the selectivity to these different products. And this is more of just like a show-off slide. These are all of these are barriers that we computed. Every number you see here is a barrier. And we computed transition states that not only involve these surface-mediated reactions where a CO bond cleaves on the surface, but also electrolyte-mediated where we have an O8, a hydroxide that's actually going into the solution. And we have some more over here. These are different C2 pathways with and without, before and after the OH elimination. We also have these electrolyte-mediated CH bond formation reactions. Instead of a hydrogenation step, the protons transfer from a water directly to a carbon atom. And we find that these steps right here actually control the selectivity. I don't want to get too much into this because I don't really want it to be a chemistry talk. But basically we find that these steps control the selectivity. And as we go to increasing CO coverage, we disfavor this OH elimination, we favor CH bond formation, and we get higher selectivity from ethylene to ethanol to acetate. And this matches the results of one of my experimental collaborators that see these same effects as they introduce CO, as they use different ratios of CO and CO2. Let's see, I think in the interest of time, I'm going to skip I'm going to move on to the next section. Yeah. Do you mind if we wait till the end? I'm kind of running low on time. Yeah, sorry. We did apply it to some layered oxyhydroxides. We found this water overlayer that forms, a very stable water overlayer, and computed ab initio thermodynamics of the different phases and edges. Okay, so that kind of sums up the present part. That's what we can do right now. Now I want to get into the future. And unfortunately, I wish I had more time for this part. I wanted to have 20 minutes, but I've only got 10. So we have this idea called the implicit quantum electrolyte. The issue is that water is more than just a dielectric. It does things like it does hydrogen bonding. It also does like long-range charge transfer through hydrogen bonding networks. So if you add hydronium, you have a water hydrogen bonds to it, but then you get also strong hydrogen bonds with other water molecules, and that kind of delocalizes the charge through these charge transfer interactions. You can also have things like water absorbing on a metal surface. Nico presented some really nice results last week where they saw that the capacitance peak on platinum close to potential zero charge is really due to this effect of these waters not just physisorbing, but really chemisorbing onto the surface and interacting by transferring electron density into the surface. And that's really why we were unable to reproduce all these quantities with a single parent value of the dielectric radius. So how do we get around this? Well, let's take a step back and consider a very simple model. Let's say we have a water, one of these explicit waters on the surface, and we don't want to simulate it with DFT. We can take a simpler approach where we develop a tight bonding model of that water. We take the water, we define these tight bonding orbitals, basically just the two lone pairs and the anti-bonding OH orbitals that are the hydrogen bond donor, acceptors and donors. And these can just be constructed from we assume like a spherical water, and we just assign spherical harmonics, S and Ps, to this water, and those basically represent these different orbitals that interact with whatever the water's hydrogen bonding to. And this is, if any of you are familiar with the Paul method, this is kind of analogous to Paul water, the projector augmented wave method that's used for, like as a pseudo-potential in VASP. Same physics. Okay, so if we have a single solvation site, we can write the wave function as a linear combination of for every band of an explicit part and an implicit part. So the explicit part is just plane waves. It's what VASP normally computes. But then we also have the implicit part that involves this tight bonding expansion where these phi's are the tight binding orbitals and the c's are the tight binding coefficients of these orbitals in each wave function. We can compute an on-site density matrix from those. We can compute an electron density and a non-interacting orbital energy. All of these have three terms: the explicit part, the on-site part from the tight bonding model, and then interference terms that are due to the overlap of these wave functions. And this is what actually leads to the hydrogen bonding. And then we can compute an energy for the whole thing. We have to include this on-site correction because similar to the Paul method, the electron distribution in this tight bonding water is not the actual electron distribution. So we have to kind of fudge it, but it works for the same reason that the Paul method works. Okay, so that was a single water that's always there. That's like a static calculation. What if we considered that the occupancy of that site could vary? Now we introduce this, we can consider two states, one with the water and one without. And we define an occupancy NS, where the occupied state has probability NS, the unoccupied has probability 1 minus NS. And now we just insert NS into all of these equations. And basically what that does is these interference and on-site terms, they basically get scaled by this site occupancy. We can define this delta N, delta epsilon, as basically the change in the density and energy, orbital energy, when we have this site occupied with water, and we just scale it by this quantity. We put all of this, the final energy expression also picks up this term, and we're able to account for the fact that that site doesn't always have to be occupied. Okay, so that's one site, though. We've only considered a single solvation site up until now, which isn't all that useful. Now what we do is we promote all of this to a field of tight binding waters. And this is where it gets kind of very unconventional. Instead of an occupancy of a site, we define an occupancy field at every point in space. Every point in space can have water occupied at a given probability and in a given orientation. We define a coordinate x that combines the position and orientation at every site in space. It's a 6-dimensional parameter. So this is it's basically analogous to a field of projector augmented wave centers at every point in space. And it sounds like this would be insanely computationally expensive. I promise it's not. It's n log n, as I'll show at the end. The other thing we do is now these tight binding coefficients, they now depend on position and orientation. So we have to solve for one at every point in space for every orientation. Okay, perfect. Yeah, so now these tight binding coefficients are also fields. Other than that, though, everything kind of stays the same. The only difference is now we're integrating over all the positions and orientations in these expressions for the electron density of a given band and the non-interacting cone-sham energy of that band. This is basically the change in electron density and the change in the energy when we have a water molecule adsorbed at a given site in a given position defined by x. And now we integrate over all those sites to get the total effect of all the waters. Basically what we're doing is we're assuming that the explicit part of the system feels the mean field configuration of the solvent. That's what we're doing, and that's kind of the approximation that goes behind all of this. One issue, though, is that now that we've promoted these, and let me just point one thing out. All of these can actually be computed by convolutions. That's the key that makes it n log n. If you look at the form of this equation, because these tight binding orbitals are rotationally and translationally invariant, because we're using spherical harmonics, that these can all mathematically be computed as convolutions. We use FFTs to get n log n. Okay, one more issue we have, though, is that if we've promoted the tight binding water to a field, tight binding waters at two positions very close to one another are going to interact. They're going to have densities that overlap one another. We don't want that. So what we have to do is we have to subtract that off. We define a hard sphere radius around every water molecule, and then we double that. That's this larger radius. And then we compute the charge density for all other explicit waters within that radius. That's this exclusion volume, this exclusion density. We basically have a cutoff function. We convolute it with the rho tilde is just the implicit density arising from all the tight binding waters together. And we get this exclusion density at every site for a given orientation. And then we just take the Coulombic interaction between this exclusion density and the actual density of the water molecule at this site, and we subtract that off. It's basically a self-interaction correlation correction, similar to what we have in DFT, that more or less subtracts off the interaction of the water at this site with all other waters that in the mean field approach go within that site where they really shouldn't be. And we replace that with what's called with an on-site correction. It's just a tight bind. It's basically a tight binding on-site correction. We also have to add some other terms. We have to add a hard sphere excess free energy that's based on a classical density functional theory. That's the kind of thing that Shankar implements in JDFPX, along with an empirical attractive energy to account for the attraction between water molecules. But these are just basically lifted off of some of Shankar's work. We can implement this into an SCF cycle. Our degrees of freedom are the explicit wave functions, which we would normally solve for in VASP. Then we have these tight binding coefficient fields. We have to solve for the value of the tight binding coefficient at every point in space, every orientation for each of the orbitals, but there are only 4 orbitals, 4 tight binding orbitals. And we have to do it for every band as well. And then we have, okay, this should be NS. I made a typo here. That's the solvent occupancy. The probability for a solvent molecule to be at position X in the orientation defined by X, because X is a combination of a spatial and a rotational coordinate. Like I said, all these terms can be computed in order n log n. We can also separate out the electrostatic effects by defining what are called excess potentials. don't really want to get into that too much, but it basically makes the method easier to converge. And then we can implement it in this SCF loop. So currently VASPsol++ has these loops here. These are the nonlinear and linear Poisson-Boltzmann solvers. But then we introduce this outer loop that also solves for these other terms, the tight binding coefficients and the solvent density. One last thing is, one thing I didn't talk about is that I said that these hydrogen bonding networks can actually transport charge over long distances. And currently we can't include that in the model, in the model I just presented. But what we can do is I came up with a way to express the pair density of two water molecules, basically the probability that a water molecule here and here are in two given orientations at the same time. And we get that by defining a correlation kernel. It's a fixed quantity, kind of like an exchange correlation hole. But we parameterize it, and then we convolute it with this what's called an S function. This S function is just a field over all space. And when we do this convolution, we get this pair density. And we can get the single solvent density just by taking the marginal of this, integrating over one of the coordinates. And then we can plug all that into this free energy functional. The one other thing we get is we get the amount of charge that's transferred in these interactions. So this is the amount of charge that's transferred from this orbital to this orbital when these two water molecules are in this particular configuration. And we also parameterize this with a function called delta Q that depends on the distance between these water molecules. It also can depend on the orientation by doing a spherical harmonic expansion. And then it also depends on the energy, the differences in the energies between these orbitals on these two water molecules. Because obviously if the donor molecule is higher in energy, the acceptor orbital is lower, you're going to get a stronger interaction. And that makes everything self-consistent. And we can solve for all of these we should be able to solve for all of these self-consistently. Okay, so that's the approach that I've developed. We haven't implemented it yet. This is just an idea right now. But now I just want to go over an outlook of where this fits in. So we've talked about bridging the gap, and this implicit quantum electrolyte allows us to bridge the gap between classical and quantum mechanics by kind of treating both in the same framework. And when I was preparing this talk, I was just thinking about some stuff, and I realized this. I wasn't even planning to say this. I'm just going to throw it out because it's interesting. But I realized that the Ornstein-Zernicke equation that describes correlations in a liquid and the coupled cluster doubles equation that describes electron correlation in chemistry, they both describe correlation, but it turns out they have the exact same form. And I think this is possibly underappreciated. If we can cast both of them into a form that looks like a Dyson equation. This is trivial. This involves more complicated math involving antisymmetrization and all that. But they have the exact same form, where T and H are the correlation functionals. V and C play the role of like a driving force, a potential. And then rho and G play the form of a propagator. And maybe that suggests that this gap between quantum and statistical mechanics really was never there to begin with. They're two manifestations of the same underlying structure. We have the Ornstein-Zernicke equation, CCD, and then RPA also has this form. It lies right in the middle. And all of these have the exact same math. So I think that we could, using this realization, we could combine all this together to create a unified framework that can describe correlation in both quantum mechanics and statistical mechanics. And that's kind of my goal moving forward. I just wanted to throw it out there because maybe it could lead to some interesting discussions at this workshop. Okay, so finally, I'd just like to acknowledge these are my grad students that did the work. Stefan Ringe, he's the one that kind of inspired me on all this because I shared my office is right across the hall from him in Munich, and we also worked together on implementing VASPsol++. He's a co-author in the paper. Richard, obviously, we've worked a lot together, getting VASPsol++ kind of integrated into the just kind of getting it out there. And then John Flake is my experimental collaborator on the CO2 electrolysis. And then if you want to read about VASPsol++, we have the paper here, and then we've got the GitHub link that you can download it.